Hello everybody. I'm excited to share our research on estimating the risk of failing physics courses using the Monte Carlo method simulation techniques. Allow me to introduce myself. My name is Isaac Caicedo Castro, and I'm a junior professor in the Department of System Engineering at the University of Córdoba in Colombia. Just to clarify, there are also universities of Córdoba in Spain and Argentina, but my institution is located in Colombia. I hold a PhD in informatics from the University of Grenoble-Alpes in France, as well as a PhD in system and computer engineering from the National University of Colombia. If you'd like to connect with me later, my contact information is provided in the slide. This project was carried out in collaboration with two colleagues. Ruby Castro Puche, a full professor in the Department of Social Sciences at the University of Córdoba, and Samir Castaño Rivera, who currently serves as a head of our system engineering department. Here's what I cover in this presentation. I begin with a brief introduction, followed by an explanation of our research methodology. Then I'll explain and discuss our main findings before wrapping up with conclusion and future directions. Let's begin with some context. Understanding academic success is an active area of research. Many studies have explored predicting student dropout, delayed graduation, and likelihood of course failures or withdrawal. Our work is focused specifically in the academic structure of the University of Córdoba. Each semester is divided into 3 sessions, each lasting 6 weeks. A key feature of this structure is that no single evaluation can account more than 40% of a session grade. As a result, the student typically face at least 9 assessments across the semester. This assessment model is designed to reduce the high stake in the final exams. It promotes a broader range of evaluation strategies, encourages consistency study habits, allows for continuous learning monitoring, enables early interventions, and ensure students receive timely academic support. The design of this system is grounded in several well-established educational theories and structural strategies, including constructivism, formative assessment, multiple intelligence theories, cognitive load theory, active learning, and outcome-based education. According to the constructivist theory, students construct their understanding through interactions with the environment. Frequent assessment allows instructors to monitor how this understanding develops over time and adapt the teaching strategies accordingly. Formative assessment emphasizes the use of ongoing evaluation throughout the learning process to track the progress, identify difficulties, and inform instructional decisions. This approach provides continuous feedback to both students and instructors, making it highly compatible with our university assessment structure. The theory of multiple intelligences suggests that the students have diverse talents and learning styles, offering a variety of assessment types throughout the semester, which creates a more inclusive environment for evaluating these different strategies. Cognitive load theory proposes that the student learn more effectively when information is delivered in manageable segments. Spreading evaluations across multiple sessions helps reduce cognitive overload and support sustained learning. Active learning encourages student engagement through tasks like problem solving, group discussion, hands-on activities, regular assessment throughout the semester reinforce these strategies by keeping students actively involved with the content. At the University of Córdoba, we follow the outcome-based education model. This approach focuses on clearly defined learning outcomes and align assessment directly with those outcomes. Dividing the semester into multiple sessions allows us to align each evaluation with the specific learning goals more precisely. Our OBE framework is integrated with the structure of observed learning outcomes or solo taxonomy, which classifies learning into 5 progressive levels, starting with the pre-structural level, where the grades goes from 0 to 2. The student has not yet grasped the key concepts in this level. The next one is the structural, where the grades range of 2.1 to 2.9. The student understands a single relevant aspect. The next level is the multi-structural, where the student understands several elements but without integration. The score of the grade is in the range of 3.0 to 3.7. The relational level, where the student integrates multiple aspects into the coherent whole. The grades in this case is in the range of 3.8 to 4.5. And the final level is the extended abstract, where the grade is in the range of 4.6 to 5. In this level, the student shows deep understanding and applies knowledge in new contexts. To pass an evaluation, a student must reach at least the multistructural level, which corresponds to a grade higher than 3.0 on a 5-point scale. To analyze the academic risks under this evaluation model, we use the Monte Carlo simulation. This numerical method allows us to simulate a wide range of possible grades scenarios informed by historical academic performance data. With this in mind, our study aims to address the following research question. What is the risk of failing a physics course if a student fails the first session? What is the risk if a student fails the second session but passed the first? And the third question is, what is the risk if a student fails both the first and the second sessions? To the best of our knowledge, no previous studies had addressed these specific questions. In a similar academic context. However, Monte Carlo methods have been applied in an educational research for related purposes, for instance, to evaluate the curriculum's effectiveness or to estimate the student motivation in learning scientific computing courses. Now, let me walk you through the methodology we adopted in this study. This is a quantitative research project based on data collected from 100 students enrolled in the physics courses at the University of Córdoba. We specifically analyzed the grades across each session and their final course outcomes. It's important to note that this study was conducted in 2024, the same year our university fully implemented the outcome-based education model, the OBE, for the system engineering department. Given the recency of the OEBE rollout and the cohort size, the data set is limited, particularly when it comes to certain combination of session failures which are underrepresented. For example, in Physics 1, there were no recorded cases of a student failing the overall course after failing the second session alone. Similarly, for Physics 2 and Physics 3, we found no instances of students failing the courses, although they failed either one of the first two sessions. To overcome this data sparsity and better explore the risk landscape, we turned to Monte Carlo simulation. This allowed us to generate a wide range of hypothetical academic performance scenarios and explore the four probability space rather than rely solely on the observed outcomes. In doing so, we assume that grades follow a normal distribution using the mean and standard deviation calculated from our actual data set. To ensure realism, simulated grades were clipped to stay within the official grading scale ranging from 0 to 1. Our goal is to estimate the probability that the student fails the course, which occurs when the final grade y is less than 3.0. Each session is denoted by xj, where j refers to the session index. A session j is considered failed if the xj is less than 3.0. The final grade y is calculated as the average of the three session grades. To quantify the risk, we compute the conditional probability that the student fails the course given that they fail a particular session. We compute the probability that of course failure given that the session was passed in the same way. Therefore, the relative risk is then defined as the ratio between these two conditional probabilities. To simulate a wide range of academic performance scenarios, we adopted a matrix-based approach. Specifically, we constructed an time tree matrix X, where each row represents a simulating student, and each column represents one of the three sessions. The value of the matrix are random numbers drawn from a normal distribution, parameterized by an empirical mean and standard deviation of the grades of each section in our data set. All values are clipped to fall within the valid grade range of 0 to 5. When then estimate the absolute risk of failing the course, given that the student fails a particular session J, this is computed by counting the number of simulating students who fail both session J and the course, divided by the number of simulating students who fail session J. To formalize this, we use the indicator function 1 of u, which is 1 if the condition u is true and 0 otherwise. This allows us to count events satisfying a specific condition within the matrix. In the same way, we compute absolute risk of failing the course given that the student passed session J, and the relative risk is then calculated as the ratio between the absolute risk when the session is failed and the absolute risk when the session is passed. This simulation-based method allows us to estimate conditional probabilities of course failure on the various performance patterns, providing nuances, probabilistic understanding of academic outcomes based on partial session results. Let's move now to the results of our research. This slide presents the means and standard deviation of the student grades for the physics course in 2024. The values mu1, mu2, and mu3 represent the average grades for sessions 1, 2, and 3 respectively. Likewise, sigma 1, sigma 2, and sigma 3 indicate the standard deviation for each session. We observe that the second session had the lowest mean, which is consistent with the box plot shown in the slide. Additionally, the distribution of final grades suggests that the students seldom fall into the pre-structural or relational categories of the pseudo taxonomy, most grade cluster around the multi-structural level. A similar pattern is seen in Physics 2, where the students perform better in the third session. Once again, final grades seldom fell within the pre-structural level. The Physics 3 course exhibit the same overall trend, confirming the consistency with the performance pattern across the three physics courses. Now, let's look at the results of the Monte Carlo simulation. For Physics 1, the simulation yield an expected final grade of 3.17, with a very small standard error and a narrow coefficient interval. As shown in the chart, the result converges as the number of simulation n increases, reaching stability around 6 million simulated students. The histogram reflects this convergence and confirms that the accuracy of the expected value. In Physics 2, the expected final grade is slightly higher than in Physics 1. Once again, the number of simulation used was approximately 6 million. The resulting histogram aligns closely with the computed mean and exhibits similarly tight distribution, reinforcing the robustness of the results. For Physics 3, the simulation shows that the expected final grade is slightly higher for the Physics than for Physics 2. Interestingly, fewer simulations were required to achieve convergence toward this expected value. The histogram clearly illustrates that the final grades tend to be higher overall this course during the simulation. As anticipated, failing both the first and second sessions correspond to the highest relative risks of failing the physics course. However, there are notable differences across the three courses. In Physics 1, failing only the second session presents a higher relative risk than failing the first session, an important distinction. This contrasts with Physics 2 and 3, where failing the first session poses a greater risk. Remarkably, in Physics 1, the risk of failing the course after only failing the second session is almost the same as the risk after failing both the first and second sessions. Let's take a closer look at the quantitative results of the simulation. In Physics 1, students who fail the first session have an absolute risk of 41.66% of failing the course. The relative risk is 2.77, meaning these students are roughly 2 times more likely to fail or 3 times more likely to fail the course than those who pass the first session. Failing the second session increases the absolute risk to 43.52%, with a relative risk of 4.05, suggesting a fourfold increase in the likelihood of course failure. When a student fails both the first and the second sessions, the absolute risk rises sharply to 62.93%, with a relative risk of 4.18, showing a substantial increase in failure probability under these conditions. In Physics 2, failing the first session leads to an absolute risk of 28.11%, with a remarkably high relative risk of 12.62, indicating that these students are over roughly 12 times or 13 times more likely to fail the course. Failing the second session results in an absolute risk of 22.17% and a relative risk of 2.49, still a significant increase in risk, though lower than for the first session. Students who fail both sessions face an absolute risk of 49.03% and a relative risk of 22, highlighting a strong association between early session failure and overall course failure. In Physics 3, students who fail the first session have an absolute risk of 10.61% of failing the course. The relative risk is 17.93, indicating a very strong link between failing the first session and failing the course overall. For students who fail the second session in Physics 3, the absolute risk of failing the course is 14.30%. The relative risk is 8.11, which is higher than the same condition in Physics 1 and 2, indicating a stronger association between the second session failure and course failure in this case. When students fail both the first and second session in Physics 3, the absolute risk rises to 33.05% and relative risk reaches 55.86, an essentially high figure that underscores the severe impact of poor performance in the early sessions. The forest plot indicates the relative risk across conditions for Physics 1, as seen. Failing the second session poses a greater risk than failing the first. The confidence intervals are narrow, and the p-value are all less than 0.05, indicating a statistical significance. The higher risk scenario occurs when the student fails both the first and the second session, a pattern consistent across the Physics 1, 2, and 3. However, a closer look at Physics 2 reveals that failing the first session is considerably riskier than failing the second. The same pattern is observed in Physics 3, where poor performance early in the course is a strong predictor of final failure. This summary table shows how absolute risk differences generally align with relative risk estimates. As expected, students who fail both the first and second sessions face the highest probability of failure. Interestingly, in Physics 1 and 3, the second session carries the highest marginal risk than the first. while the intervals in this table are slightly wider. The p-value remains below 0.05, affirming the robustness of the result. Now I'll draw conclusions and future perspectives. We employed Monte Carlo simulation because the data set we collected was small and statistically unstable, with some failures scenario leading to undefined and highly variance risks estimates due to division by zero or near zero denominators. The Monte Carlo methods offers a data-informed but smooth approximation of the risk landscape, simulating what outcomes might look like if we have a largest data set with similar statistical properties. These findings can inform instructional planning. Teaching staff and lecturers might consider restructuring course content and support strategies to mitigate the risk of course failure, particularly in light of the observed probabilities associated with performance in each session. In Physics 2 and 3, failing the first session is more critical warning signs than failing the second. This may reflect psychological or motivational dynamics. A student who begins a course with poor performance are more likely to feel discouraged, disengaged, and less resilient in the face of further academic challenges. More broadly, early academic performance in the first and second session is strongly associated with final outcomes. These patterns go beyond statistical correlations. Early struggles may reflect underlying motivational, behavioral, or cognitive issues, making them valuable triggers for early interventions. Future research should aim to design and test target support strategies to help students recover from early setbacks and improve their academic trajectory. This could involve personalized feedback, peer mentoring, counseling services, or adaptive learning tools that respond to student individual performance patterns. In Physics 3, a student who passed the first two sessions face most negligible risk of failing the course as a result. Some may become complacent and neglect the final session, believing the sources is already secured. Conversely, students who fail the first two sessions encounter the substantially higher risk of course failure. This discrepancy points to a potential imbalance in the difficulty or weight of the sessions. Simulating alternative grading scenarios could help inform course designs and promote more balanced learning and improve student success rates. We also observe consistency improvement in student performance in Physics 1 and 3, reflected in the higher average grader and lower absolute risks in the later courses. This trend may result from students gradually adapting to academic exception or developing stronger study habits and disciplinary knowledge over time. However, it is important to note that in the system engineering program and at university, students are not strictly required to follow a prerequisite sequence for physics courses. For instance, a student may enroll Physics 3 without having completed Physics 1 or 2. While most students do follow the recommended progression, exceptions do occur. Unfortunately, this study did not include information on these atypical cases, which may be a factor in interpreting the results. The use of Monte Carlo simulation methods have proven highly effective for estimating absolute and relative risk of course failure. This approach supports evidence-based decision-making in academic planning and policy design. Grades were generated using a normal distribution with parameters derived from real student data. Although our data set includes relatively few failing cases, simulating performance probabilistically allowed us to capture rare but plausible outcomes, ensuring a realistic and representative analysis. For further research, expand the data set by collecting additional student records to this SN methodology to other courses, thereby broadening the scope of the academic risks. Besides, we shall refine the simulation model to incorporate the specific evaluation structure and coursework design in each session. This will allow for more accurate risk estimation. We shall adapt a simulation framework to account for non-uniformization weight in the calculation of final grades, with the aim of minimizing failure risks through alternative grading schemes. Integrate bootstrap resampling techniques to estimate the variability of simulation parameters such as means and standard deviations, thereby enhancing the robustness of our risk estimates under condition of limited data. Thank you very much for your attention. If you have any questions, this is the Q&A session, but this is a virtual presentation, so if you have any question, please don't hesitate to let me know. You can email me using the information that I provide in this speech or in our paper. Once again, thank you very much. To the next time.